Hello everybody, my name is Adam Warski. Thank you very much for coming. I come from Warsaw, Poland, and I would like to talk a bit about a library I've been working on called sttp, which is a Scala HTTP client. So there will be a couple of slides, but most of the talk will be live coding. If you would have any questions or would like to see any particular aspect, just let me know during the talk and we can always try it out live. Okay, so if you hear about a Scala HTTP client, especially a new one, you may start to wonder why would anybody actually do that. There's quite a lot of those out there. For example, there's Dispatch, which was historically the first one out there. It was the original version was using a number of symbolic methods, so people kind of made fun of it a bit. Now it's changed. There's PlayWS, which is now a standalone library, also an HTTP client. There's Akka HTTP, which also has a client component. There's ScalaJ and a number of other libraries. However, all of these libraries, they take different approaches to what API they offer, what execution models they offer, and so on. And so every time I was using one of those, I was lacking in some respect, especially on the API side. So I always thought that the API, the way you actually interact with the library could be better. So here's my take on how we can actually try to make the API better. So there's a couple of main assumptions behind the projects and how the API is designed. The way we describe requests, so that will be the main part of how we work with the library. So the request descriptions should be immutable, so that you can freely share them in your code. But it also means that once you have a request description, you can treat it as a template and then customize it in multiple ways, right? And reuse the same template in multiple instances. So we would like to support both synchronous and asynchronous execution models. So sometimes the synchronous way of executing requests, the blocking way, is the most convenient one. Like if you are trying to explore some API, right? You just want to fire a request and get a response, and that's it. Sometimes you are working in a future-based environment, so you actually want to have asynchronous execution. But first of all, the API should be programmer-friendly, meaning that it should be easy to use, simple to use. It should be discoverable, like using autocomplete, pressing dot and then getting list should give you the methods that you would expect, and the methods should actually do what you expect them to do. And finally, the request description, the definition of the request, should be separate from the way the requests are executed. That's also connected with the various execution models. Okay, so these are the goals. Hopefully, we'll be able to see at the end of the presentation if they are in any way successfully realized or not. So before we jump into code, just a brief introduction of who's talking to you. So as I said, my name is Adam Warski. I'm the co-founder and the software engineer at SoftwareMill, which is a custom software development company in Poland. We work with a lot of US clients, also with clients from Europe. We use quite a lot of Scala and Java and other languages in various domains. Recently, quite often, it's blockchain projects or machine learning projects. We also send out Scala Times, which is a Scala weekly Scala newsletter. If you don't know about it yet, check it out. I'm working on some open source projects. sttp is one of them, and sometimes I'm writing things on our company blog, which is over here. So also feel invited to visit it. Okay, so that's it for the introduction. Now let's actually start coding. So we'll create a Scala class with a very unimaginative name, New York. It will be an application. So the first thing that you need to do when you want to work with STTP is actually import the package. So you import com/softwaremill sttp._, and this gives you access to the basic request definition and all the builder methods which we will use to actually describe the request that you want to send. Okay, so let's describe a very simple request. The the starting, the empty request that we will always be using is called sttp. So that's an empty request description. Okay, so that's like a very basic request template which we can customize further. So we start with sttp, and now we specify that we want to send a get request to the given address. The address will be HTTP. We'll be using a local server, just in case internet doesn't work, and the local server is running on port 823. It has a couple of endpoints which are just mirroring the input so that we can see that it's actually working. So we will be hitting the echo get endpoint. We can actually see how the server is implemented. It's over here. It's an Scala HTTP, but that doesn't matter. So you can see that here is the handler for the echo path, right? If you get an echo request, we should get a response containing all the parameters and the path. So we will see if that works. Okay, so going back to our request description, we want to get the following address, and that's it, right? That's all that we actually need to do in the simplest form. So that's a request, right? A request. So far we have only, so when we actually invoke the get method over here, we just create a description. Nothing happens yet, right? So to actually send the request, we need a way, we need some object which will actually specify how the requests are sent. And that's implemented in a backend. So here we will be using a very simple synchronous backend, HTTP URL connection backend. Okay, that's built in. It uses the HTTP URL connection class which comes from every Java, and it's a synchronous backend, meaning that it's sending requests in a blocking way. So now that we have both the request description and a backend, so which tells you how you can execute requests, we can actually send it. So we'll print line the results request.send. Okay, the send method over here takes an implicit parameter which is the backend to use. So we will be using that backend, and as a result we will get we will synchronously get a response. So let's print out the body and let's try running it, and hopefully it will work.
What's it called on site?
You will see later. You will see later. That's a very good question. You will see later. Yeah. And yes, it did work, as you can see over here. Okay. So that's only one example of a backend, of a synchronous one. So it's not very exciting. Let's now try using a different backend. So let's comment this out. We can now use another backend. So now let's use the Scala HTTP backend. Okay, so now this backend is different. You can see that the code here stopped compiling. And that's because the Scala backend actually sends the request in an asynchronous way. So before we had the synchronous backend, which was doing blocking calls. Now we have the asynchronous backend, and with that backend, the result of the send method will actually be a future. Right? We will get the response sometime in the future when the asynchronous request completes. So to actually do that, we need to create a for comprehension. So to get the result, we will map over the future request.send, and here we will simply print line r.unsavebody. Okay, and once we are done, we will close the backend because there's a thread pool over there which needs closing, otherwise our program will never terminate. So let's try running that. There's an implicit error because I forgot Scala concurrent execution context implicit global, or any other execution context. And it starts a bit longer because the thread pool needs to be started, but the result is the same, right?
You don't need an active system for this?
Sorry?
You don't need the active system?
So if you use that form of creating the backend, it will create an actor system for you. If you have your own actor system, you can pass it here as a parameter.
So your library depends on other HTTP client?
So there's a number of backends. the core library doesn't depend on anything. It only depends on Java, but it only provides the HTTP URL connection backend. Okay? There's a module which depends on Akka, and it has the Akka HTTP backend. There are also other backends which I will show later. But yes, well, obviously, if you want to use the Akka HTTP backend, it uses the Akka backend. An important thing about STTP is that it's not really an HTTP client. Okay, it's a wrapper around a number of other HTTP clients, such as Akka HTTP, Async HTTP client, OK HTTP. Right, so all the hard work is delegated to the existing backends, which differ in the implementation details. What STTP provides is a unified API and a way to describe the requests. Okay, and we also can send a more complicated request. So for example, let's say we want to send a post request, so we will use the post method, and here we can change the endpoint to post, which will accept a post request, and we can set the body to hello Scala Days. And we can again try running it. So you can see that like sending a post with a body is exactly how you would expect it to be done, right? You use the post method and then you specify the body with the body method. So nothing very complicated. Okay, so let's once we have the basics done, let's jump for a bit to another topic, how the addresses over here are created. So you might have noticed that I'm using the URI prefix over here, right? So what does it really do? So let's comment it out for now. So you probably know string interpolators, right? So you can write s, and then if you have val x equal 10, this is 10, right? And it will, so the string interpolator will embed, will enable embedding of values into strings, right? And you can write your own interpolators, and in this case, there's a URI interpolator, which has some features specific to constructing endpoint addresses. So the simplest form is you just write an address, right? So what this will actually give you is an instance of the URI class, okay? Because we are using the interpolator, the result is an instance of the URI class. We can see what the URI class is. It's actually a case class containing all the things that you would expect from the description of an address, right? So we have the scheme, the host, the port, and so on. So you can, of course, if you want to specify the address over here, right? You can create the URI instance by hand, or you can use the interpolator over here, which will give you an instance of that object. Okay, but so far it's not very interesting, right? It can only parse it can parse a literal string, so that's not very exciting. So let's try actually embedding some parameters, right? So of course, you probably expect that we can actually embed parameters, we can embed values as before, right? Where this gets more interesting if the values contain some special characters, right? Such as hello world, right? So of course, the space, the white space isn't allowed in a URI, it needs to be escaped, and that's exactly what happens. So we can see that the result actually uses the plus, right? Which is the proper way of encoding a space. It's also context sensitive, so if we use the same value as a path component, this space will be encoded using the percent encoding, because that's what the specification says, that the white space needs to be differently encoded depending if it's in the query or in the path. Okay. So far, that's like the very basic functionality, but it doesn't end over there. So quite often we have multiple parameters. Let's say we have 2 over here, and some of them might be optional, right? So we might end up, gluing together the addresses and adding the question marks and the ampersands, depending if the parameter is there or not, if it's the first parameter, the second, and so on and so on. Here you can have it automatically. So if we have an optional parameter, let's say this will be an option, let's write an option of int. So here we have an optional parameter. Here the parameter is defined. So if the parameter is defined, if it's a sum, it will be simply used in the address as is. However, if the parameter is none, the parameter will be removed. And as you can see here, the URL is properly formatted, right? So the dangling ampersand is removed, and it works also nicely for multiple parameters, right? It will work as expected, right? Same thing if you have a map of parameters. Let's say p1 is 10 and parameter 2 is 20, right? So we can simply embed the whole map over here, and it will do the right thing, meaning it will actually expand the parameters into a proper query. And this works in many other contexts. So we can have a list of path, will be a list of x, y, z, and we can use this as the path over here. Again, it will be unrolled into the path as you would expect, right? So that's the way you can create addresses. I think quite conveniently using the URI interpolator. You can interpolate so you can embed values in any part of the URL, the scheme, the subdomains. The subdomains can also form a list, the path, the query, and the fragment. So all of that is supported. Okay, so now we know how to create addresses. Let's go back to actually sending some requests. Let's comment that back in. So we have seen a couple of methods for building requests, but usually, of course, the requests are much more complicated, right? So there's of course a number of other methods which actually allow you to build. Where they have my notes over here. There's a number of other methods which allow you to specify how the request should look like. So, for example, we can specify a header, x my header, and the value will be like anything, right? We can specify also. So you can see that there's a number of these methods. Anything like content length, content type, and so on and so on. But what's quite specific to HTTP is that you also specify how the response will be handled, right? So by default, the response is always read into a string. That means that there's no danger of, if you don't forget to consume like the output of the request, there's no danger that you will leak some resources. So the way the response will be handled is part of the request description, but it can be customized as well. So we can say that the response, for example, should be ignored. So this will discard the response. We can say that it should be saved into a string, which is the default. We can say that it should be saved to the file, and there's a number of other ways to do it. So let's say we can, for example, say that we want to get a byte array, right? So there's a number of these methods that you can use to customize the request. Another nice thing is that you can use these methods in any order. So it doesn't matter what the ordering here is, meaning that you can create a request template with any characteristics of the request specified and specify the rest later. Okay, so that's how you create templates. Okay, since we are at the handling the responses and setting bodies and getting responses. So if you want to set a body, you also have quite a lot of options. So you can, for example, send a file, you can set a byte of array, an input stream, a string, and so on. But also, quite often nowadays, you are working with various streaming libraries, right? So you maybe have an input stream that you actually like a reactive stream of strings, bytes, or whatever, which you actually want to send to the server. So how do you do that? Well, there's no variant which will actually allow you to send a stream over here, because there's no standard way of sending a reactive stream in Java, right? You always need to. So there's akka streams, which is one way, but the Monix streams are also reactive, but they have completely different interfaces. So there's no like way to do it in a generic way. So you have to actually specialize for each of the backends. So how do you do that? So let's say we have an akka stream. We'll be using akka here. The akka stream will be a very simple one, but just as an example, it will be an akka source using a byte string, which is the byte array, which is better than a normal byte array. Hello, it will consist of 2 segments and a byte string akka. Okay, so that's here we have defined an example stream that we want to send as the body of the request. Okay, so to actually send that stream, we now have, let's remove those because these are not important for the example. We'll be using equal post, that's fine. Okay, so now instead of the body method, we have to specify that it's a streaming body, so we will use the stream body method. And we'll get a new request description, and I think if we actually try to run it, why is it red? There's the backend.
Which one stream in your stream body?
Oh yeah, right. Thank you. Yeah, now it works. So it's good that it didn't compile because the type was wrong. So we can see that it actually received the whole stream as we have specified, right? Okay, so since we are at the types, you may be wondering how does it know like which types of stream are supported and what are the response, like why are we getting a future if we send using the akka backend, and why are we getting a synchronous response if we are using the URL connection backend, right? So this is all part of the backend type. If we take a look at the akka HTTP backend, for example, let's look at the definition at the top over here. You can see that that's the backend implementation, and somewhere over here it extends the STTP backend, which is like the base trait that every backend has to extend, and that backend has
Question: can you go back to your previous example?
Sure.
When you were trying to send that stream, you had HTTP URL connection backend, not the akka HTTP backend. The question is, how does it know that it is an akka stream because your backend was different?
I will. That's what I was going to show. If we try to use the HTTP URL connection backend, and we try to send the request over here, okay, that's it actually won't compile because the URL connection backend doesn't support any kind of streaming. So this will only work if we actually use the akka backend, and I will explain exactly how that works right now. So now we can see that it compiles because we are using a backend which supports this kind of streams. Okay, so how do you know which kind of streams are supported? If we go to the backend definition over here, right, you can see that the type of the backend, it extends STTP backend with 2 type parameters. The first type parameter is the wrapper, in which the responses are wrapped. Okay, so here it's a future, right? Because every response will be wrapped in a future. And the second type parameter is the type of streams that are supported, right? So this means that this backend will accept a request, or can send requests which might use this type of streams, either as to send the body or to receive the response body, right? So that's the streaming type it supports. And that's how the responses will be wrapped. If we take a look at the HTTP URL connection backend, okay, it's a bit simpler. It doesn't support any kind of streaming. So the second type parameter is nothing, and the wrapper is identity. So it's like no wrapper at all, right? The identity wrapper is again a very simple definition, just a type alias. Okay, is it clear how that works? Okay, good. Now also other, as I've mentioned, for example, there's the async HTTP client Monix backend. So this backend will wrap responses in Monix tasks, right? If you have a programming stack which uses Monix and not Akka, right? You can use the same API to define the requests, and whenever you send the request, the response will be wrapped in a task. And the streaming it supports over here are the Monix observables, right? So you can set the body, which is a Monix observable, and you can receive the response as a Monix observable as well. But you have to use that backend to make this actually work. Okay, so that's the typing of the backends. Now let's move on. Right. So now we know how the types on the backend side work. What about the types of the request, right? So far we have defined a request, but we didn't see the type of the request. And the type of the request is the one slightly complicated thing in STTP. So this compiles fine, right? We are trying to send a request, we have specified the endpoint and so on. However, if we try to comment out the method which specifies the endpoint, so if we comment that out, the code will actually stop compiling, right? Because you can't really send a request which has, maybe it has some header specified, maybe it has the body specified, but it doesn't have the endpoint specified, right? So that's clearly an error, and you will get a compiler error, and the error actually says, it's probably too small for you to see, but the error actually says that this is a partial request, the method and URL are not specified. So there is even some user friendliness over here. So how does that work? So what does the post method do that it stops code from compiling? So let's try writing down some type request definitions. So the simplest request, R1, which is the empty request, will have type request. It will have type partial request, which is a type alias string nothing. Okay. So we have two type parameters here. Again, going from the end, that's the type of the streams that the request requires from the backend, right? So here we don't have any requirements on the backend as far as streaming is concerned, right? So it's a nothing. This type parameter specifies how the response will be handled. So that's the type to which the response will be read, right? If we now try to use a response as byte array, this will change this type parameter. Right, so now we have to change this type parameter to byte array. If we try to use a streaming body like this, now we have to change this to a source of byte string not used, if I'm not mistaken. Let's see. I never remember the Akka types. Any. Okay. Any. Okay, so this compiles as well. So these are the two type parameters of a partial request, right? Now, if we so let's actually remove that. Let's use the starting request. So this will be a partial request of a string nothing. Now, if we actually specify the endpoint, like over here, right? This will stop being a partial request because now the endpoint is specified and it's a request which we can actually send. So it will now become a full request, again with the same type parameter specifying how the response will be read and the streaming requirements, right? And now the send method over here, it has a restriction that the self type needs to be a request, not a partial request. Okay? How does that work? Well, the request type is actually a type alias, so that's a type alias for RequestT ID. So there's one more type parameter. So the full request is a RequestT where the first type parameter is identity. Okay. Now a partial request let's call it R0. It will be empty, string nothing. Okay. A partial request will be a RequestT where the first type parameter is empty. Okay. And this type parameter specifies how if the URL is specified. If we go to the RequestT case class, again, it's a very simple case class. So once you actually create the request description, you can inspect everything that you have over there. So you have the methods, the body, the headers, some request options, how the response should be handled. So all of that is part of a simple case class which you can inspect. And you can see the 3 type parameters over here. Right, so going from then, that's the streaming requirements. That's the type to which the response will be read, and this type parameter specifies if the URL is specified. Right. So if this U over here is an identity, so if we substitute identity, for example, over here, right, we'll simply get a URI. Okay. If the U over here is an empty, and empty is an alias. Is a container which is always none, right? So if that U will be empty, that will resolve to none, meaning that the URI is not specified. Okay, so that's the whole trick. And finally, here in the send method, we have a restriction which is an implicit witness specifying that. That the U type parameter must be identity and not, for example, empty. Okay, so that's just you don't really need to know exactly how this works to use the library. It's just so that you have the full picture.
Question.
Yeah.
Can you go back to that other line? Where your case class definition?
Okay. At the top. Yeah.
So why is it not covariant around T? Should not be covariant on that. Parameter?
Oh, the streaming.
Yeah, no, T. T is your thing that it takes, right?
T is the type of the response, how the type to which the response will be read. Okay, the thing here needs the plus, so that even if you have a backend which supports streaming, you can still send a request which doesn't require any kind of streaming. Okay, so that's the types of the request. So if you need to, you can always write down the types of the request, of course, as well. I think it's slightly complicated, but it's still hopefully possible to understand how that works. Okay, so let's see. We don't have that much time left. So let me maybe show you how you can actually, and the errors that John was asking about. So errors are quite common in HTTP, right? When you make a request, there's quite huge chances that the server will be down or something like that. So let's see what happens if we try to actually hit an endpoint which isn't found. Let's use the synchronous backend just for simplicity. Okay, so request send.unsafe body, print line, and without a streaming body, just a normal body. No, without any body at all, and it will be a get. Okay, that's what our endpoint supports. So now we are trying to hit an endpoint which will return a 404, right? And you can see that we get an exception, right? Because status code 404, the requested resource could not be found, right? And why is that? Well, we have, if you try to get a resource and you have specified how the response should be handled, right? You have only specified how the response how the correct response should be handled, right? The error is usually a string, like in most cases, right? So even if you want to save the response to a file, if it's a 404 or like a server error, you probably don't want to do that, right? You don't want to handle this 404 message as a file content, right? So that's why the exception is, and that's why the method is called unsafe, right? Because it might throw an exception if the server responded with an error. The safe way to do it is to use the dot body. The dot body will actually return an either. Okay, so you can see that here the either is a left, right? Because the response was unsuccessful. We got an error, so it doesn't matter how the body is deserialized. So we can say that we want the response as a byte array, for example. This will actually always be a string, right? Because it's usually the error message. If we now try to hit an endpoint, which will be a proper one, echo get, we will actually get a write value over here. Well, with the byte array, because that's how we wanted the request to be read. Okay, so that's how you handle errors. Okay, another quite important thing is testing, right? So, well, we can send the requests nicely if we have the network, but then in the test you probably don't want to actually send the request over the network, right? So you need to have some way of actually testing that the descriptions of the request that you have defined are correct, okay? And that's where there's a special backend. It's called the sttp backend stub, and this allows you to create stub backends which will mock some responses. So we can create a stub backend for any kind of wrapper. So if you're using a future, it will be a future-based backend. If you're using task, it will be a task-based backend. Here we'll be just using a synchronous backend. And now we can specify the behavior of the stub. So we can say that when the request matches. So if we make a request where the path uri.path starts with a list of x, y, right? Then we want to respond with OK. And when the request matches that the header, oh no, that's specified the header. Let's say that the URI path starts with, let's say, z, then we want to respond, then respond not found. Okay? So that's our stub, that's our backend stub, and we can use it instead of the normal backend. So we can now actually print line request.send. Okay. Let's now send a request to xy, right? So this should respond with a 200 OK, and it did, right? We can see the 200 over here. Oh, by the way, I didn't show you the response class yet. So the result of the send method is a response which is wrapped in the appropriate wrapper. So the response again is a simple case class, quite easy to work with. It has the status code, it has the status text, it has the headers if you want to access the response headers, and the body of the response to whatever it's deserialized. If we now try to send a request to an endpoint which is specified here in the second stub definition, you can see that we got a 404, right? So that's quite a useful thing for testing. If you have the request description, you can, as always, it's an immutable definition of how the request should be done, and then we can use various backends. So we can use a normal, like an Akka backend, Monex backend, whatever, for your normal work, and you can use the stub backend in tests to actually test that the request definition is correct. Okay, one last thing which maybe I showed before summing up is how to specify custom, so how to deserialize to custom types and to custom and how to send custom bodies. So we can actually let's remove that. So we can actually customize how the responses are deserialized. For example, let's say that we want to deserialize the response into a list of strings, which will be the words from the response. So we can create a new specification of how responses should be handled. So we can call it as words, and the as words will take the as string response, which reads the response into a string, and then we will map over it and splitting it by spaces, right? And now this new specification, it has a type which is a response as of list of string, and again the streaming parameter is always over there, the second one, and we have to convert that to a list, right? And now we can use our new specification of how responses should be handled in our request definition. So let's echo get, and we can actually now run it, and it will actually give us a list of words, right? So the response, why is it? Oh, because I sent it twice. Okay. But you can see that over here you actually have a list, just as we have specified in the request. The type of the request will also include the fact that the response will be read into a list of strings. In a similar way, you can create body serializers, so you can create a serializer which will accept a case class and serialize it to JSON, for example. There are integrations for that. So just to give you an overview of what are the available backends. There's quite a lot of documentation on how to actually use it. Here's a list of all the backends. You can see that we have used the HTTP URL connection backend, and we have used the Akka HTTP backend, but there's a number of others. So if you are working in a Scala Z stack, a CATS stack, a Monix stack, you can choose a backend that probably matches whatever you are doing. So there's quite a lot of possibilities over here. It's also quite easy to create your own backends. So for example, if you want to add some logging or some metrics, you can actually create a custom backend wrapper, which will actually, before each request, start a timer, and then after the request completes, stop the timer, report it to your metrics server. There are some built-in integrations with Prometheus and with Brave, so you can just use that. Okay, so I guess going to the summary right now. With HTTP, the basic thing you get is a hopefully programmer-friendly API to describe requests and to define how the request should be sent. It supports everything you would actually expect from an HTTP client. You have the URI interpolator for easily creating the URIs with optional query parameters, paths, and so on. It supports compression, cookies, sending form data, uploading, downloading files, sending multiple uploads, doing authentication, redirects, and so on. So it's all over there the way you would expect. You can, yeah?
You say it supports compression. Are you saying it supports gzips?
Yeah, so if actually we go to the definition of the empty request, it's not really an empty request, but it's a request which always accepts the gzip and the zip encoding, and the responses are decoded automatically.
Support HTTPS?
Yeah, sure. Yeah, of course. Yeah.
Does it support WebSockets?
So the question is, does it support WebSockets? No, WebSockets are not supported. It's actually quite a common question, but it's would be probably a separate project, and I'm not sure if it would be at all possible to abstract WebSockets in a way that it would be possible to implement them using either Akka or some other backend. So yeah, for WebSockets you have to stick with the native clients and what they offer. Yeah.
Does it have any built-in retry mechanism like exponential backoff?
Does it have a retry mechanism? Not yet. There's an issue to actually do that. And you can, but the way you would do it is to create a backend wrapper which actually retries the request. I think there's an example you can see that in the documentation there's actually an example of a very simple retrying backend, so how you can do that. A more advanced example, like it probably could get into the main code base, but if somebody would like to try, of course, pull requests are always welcome. Okay. And we have the various execution modes, right? So we can either do synchronous or asynchronous requests depending on which backend you use. And remember that all the hard work is actually done by libraries which are there for a long time, such as Akka HTTP or async HTTP client. So I don't think there's any sense re-implementing that. However, the API is hopefully quite nicer. And HTTP is like I think I've created a couple of libraries which have a common theme, and the theme is to use simple code to use simple problems. So I think sending HTTP requests is actually quite a simple thing you might do in your code, and the code should be quite simple as well. And hopefully STTP fits in that description. I've also written a blog about that, trying to motivate how that could work. Another example of a library which would hopefully provide simple code for a simple problem is QuickLens. That one which allows you to modify deeply nested case classes in an easy way without having to write multiple copy statements. And that's all I had. The library is open source, so of course please check it out on GitHub. If you would have any suggestions, create issues, there's a Gitter channel. The presentation is online here as well. And yeah, I don't think I have any time for questions, but I'll be here until the end of the conference, so feel free to ask me either here or online later. Thank you.